All right, so our last speaker for the day is Abel Guada Azze. You can go ahead.
Okay,
Yeah,
thanks.
no problem.
Thanks, all of you for being here and making this possible, especially those of you who are really jet lagged like me. I'm kind of running on low battery, especially at this time. So I'm going to talk about how to optimally stop a Gauss-Markov process who has been forced to hit a terminal density at the end. I come from Madrid. Cunef Universidad is it's a super young university, so I don't expect you to know it yet. And this is a joint work with Bernardo Dauria from University of Padua. So I dropped this quote that I actually read a few days ago from Cathy O'Neill's book, Weapons of Math Destruction. It's a pretty good read because I thought it illustrated pretty good what we do here, which is models are opinions embedded in mathematics in the particular sense that it should be, they should be allowed to be shaped and reshaped by the beliefs we have, okay, and the data that we get to see. So in that sense, let's imagine that this process represents the evolution of a price, and you want to choose the time to sell optimal that asset or sell financial instrument written on top of that or whatever. But the added thing here is that you are imposing that belief that you have on the terminal density. In this case, for illustration's sake, is a mixture of normals. And on top of that, that blue density is the updating that you do on your prior based on the evolution of the process, okay? So that's what we want to solve. You can embed that in an optimal solving problem. So if you think about it, you really have here two ingredients, the unconditioned process and the pinning point, which is random. And you can merge both in the same probability space to force the last point of this guy to be the spinning point, which has the density you wish. And we call that randomized Brownian bridge, okay? Now, you have to agree on a model for this guy, preconditioning. And we chose Markovian and Gaussian at the same time. Markovian because then you can take advantage of all the Markov setting in optimal stopping. And Gaussian, because when you add that, you achieve kind of a good threshold between flexibility and tractability. These are illustrations of Gauss-Markov processes without conditioning. So it's really like time-dependent Austen-Uhlenbeck. You can control this volatility, time-dependent one, and then it's linear in space, the drift. And we have these other 2 degrees of freedom that you can play around with. Actually, these are 3 pictures. These dashed lines are minus beta over alpha, okay? Or there. So that is like, it's like either the pulling or the repelling level. So the process is either attracted or repelled towards that level based on whether beta is negative or positive, okay? And the absolute value of that is that force or of pushing or pulling from the beta, okay? So this is what we want to solve. Want to solve the optimal stopping times, finite horizon, and this expected value. The SOPRA index here is it reflects that you want to end up with that terminal density nu. This is the process starting time t value x. So we want to find a tractable enough characterization of V, of course, more tractable than what Dinsky's characterization says, and find the optimal stopping time. If it exists, in this case, it does. And that boils down to finding the stopping set or the boundary of that stopping set, the optimal stopping boundary. So I'm going to guide you through these 3 problems increasingly. First, we're going to start seeing what happens if you work with the unconditioned Gauss-Markov process to see if you can say something that basic scenario. Then we're going to move on to conditioning deterministically at the end. So that's a classic bridge. And finally, we're going to see what happens in the general case, randomized Gauss-Markov bridges. So regarding the first problem, we work that we call it time-dependent Austen-Uhlenbeck bridges. It was published a year ago, and we apply it to the optimal exercise of an American option. This was actually the problem we solved. So again, gain function coming from the optimal exercise of American option is the strike price, discounting, exponential discounting, lambda is the discount rate, and these are the dynamics. Now the process is always attracted towards alpha. This guy is positive. This is like the pooling level, and these are the volatility. Now, when we saw this initially, we went to the literature to kind of find the solution out there. We didn't find it, it wasn't. We found some few papers working on simplification of that problem, mostly the time homogeneous version, the classic Austin-Uhlenbeck bridge. Then later on, we realized that the time in homogeneous component was the added difficulty here. This is kind of a loaded slide. This is like the solution method. To comment briefly, no stepping into details due to time constraints. But this is the bulk of the paper. The majority, tons of pages just summarized in this slide. So you prove regularity of the optimal stopping boundary. It's a time function, and the stopping set is everything below that time function. It is bounded. You can find the last value of the optimal stopping boundary. You move on to prove regularity of the value function, higher smoothness, bounds for the partial derivatives, the free boundary problem. As you know, you need this extra condition because this free boundary problem, you don't know what the boundary is. You need this extra condition to guarantee uniqueness of the solution, and that's where things get more complicated in this case, because we're not in the typical framework, and we already had a couple of talks about that. What happened with if the boundary is not monotonic, you know that it's monotonic, you can get the smooth fit condition. The idea is one way of getting the smooth fit condition is proving this probabilistic regularity of the boundary, which is if your process after starting at the boundary immediately hits the stopping set, you're good to go. You can prove the smooth fit condition. So for monotonic boundaries, you have that. It's not our case. The next thing we thought about was piecewise monotonicity. We are there, we believe, but we couldn't prove that. And then we went for Lipschitz continuity. We found that paper of Tiziano talking about the Lipschitz continuity of the boundary, and we thought of extending that to our case. It wasn't immediately applicable, but we did it. Lipschitz continuity allows you to prove probabilistic regularity of the boundary, because basically what you're saying is that you cannot evolve the boundary with infinite slope, and your process does, because the law of the iterated lowering, so you immediately hit the stopping set. And now we get the smooth fit condition, apply a station of Ito's formula, which is, you can find many of those extensions here in this wonderful paper of Goran, talking specifically about Ito's formula applied to problems of optimal stopping. So you get the free boundary equation, and this is the solution in just one slide. So best time to exercise, you step below the boundary, which is characterized by the unique up to some regularity condition of this Volterra type integral equation, and the uniqueness follows like is common in this type of settings when you end up characterizing via Volterra integral equation. Follows the steps of Goran's paper on the American Ocean problems. So value functions and integral of the boundary, a kernel, super non-linear, but explicit. And as you know, the problem here is you don't know how to find this guy explicitly, but you can apply some numeric methods. Picard iteration algorithm is the standard way to do it. So these are just images of the boundary in this case, so you can see the non-monotonicity. And actually, you can play around to have as many inflection points as you want, play around with the time dependency of this guy. So these are the dynamics. For illustration's sake, we set the volatility equal 1, and then here we fix the pooling force, right? The pooling level alpha. This is higher one, lower one, and then this sudden change. We use this distribution of a normal 0, 1 to represent going from one level to another in a rapid but smooth way. You can see how the boundary also inherits that attraction. It's similar here. This is an exponential attraction level, and then you play around with being more attractor, less attractor, or introducing a change of attraction rapidly. Okay, so that's it for the time dependent Austin-Uhlenbeck. So next step to see if we guys still say some things about knowing the terminal density or imposing a terminal density is what happens if we bridge deterministically. We do that where we work out the solution. This paper was recently published in January. So the idea, I got this error. I don't know why. This document is trying to connect. Oh, plenty you can click. So now this is the optimal stopping. We chose identity and function because at the beginning we wanted to isolate the complexity just in the process, but you can extend that if you control the partial derivatives of your gain function, you can extend that to more general cases. So again, we looked in the literature, we just found the Brownian bridge case and some deviations from the Brownian bridge, but not that much. This is just a few papers. There are more than that, not too many more than that, but there are more than these three. And so the idea is, okay, we are still in the non-monotonic case. Perhaps we can do the same trick, go for Lipschitz continuity. We try to do that, but we hit a wall because the explosion of the drift of bridges that you have. So we couldn't apply some techniques, but at the end, what we did was we came up with this characterization of this representation of our original process in terms of a time transformed Brownian motion. So it's a Brownian motion. This is a change of time. You're also changing space with these functions alpha and beta. And so basically what you're doing is equating your original process to a Brownian motion through a linkage function, which will end up being the gain function of this equivalent optimal stopping problem. Okay, so this is the original optimal stopping problem. This is an equivalent one, simpler in the sense that now you have infinite horizon, and this guy is a Brownian motion, but more complex in the gain function now because you have time dependent one. But what was here troublesome, which was the explosion of the drift, was equated to the explosion of the Brownian motion as time goes to infinity. And you know how to control that using the law of the iterated logarithm. So we control that explosion. You establish equivalence between the optimal stopping times. And now you can go back and forth. You get the solution of one is equivalent to getting the solution of the other one. Okay, so we can apply the same solution method, way more quite different in many aspects, but I'm not going into details. So this is the solution. So we also managed to characterize the optimal stopping time as being the first time to step above the optimal stopping boundary, characterized by integral equation. And then the kernel, it's kind of the same idea, applying Picard iteration algorithm, going back to these highly monotonic boundaries. So this one, for instance, is now these are the dynamics of the precondition process. Is volatility equals to 1 to illustrate what happens if we change these two guys here. So the non-tilde process is the bridge made by forcing the tilde 1 to stop at 0 at the end. And here we are fixing pulling force, varying the pulling level. And so you can see again that the boundary inherits that. So this one is designed to illustrate, I don't know, perhaps some seasonality. You can see how the boundary also inherits those waves. This is baseline, and this is a sudden change of pulling level. So kind of the same idea here, but the other way around, fixing the pulling level, varying the pulling force. This is like more and more attractor over time, less and less attractor exponentially. And this illustrates that you have some baseline levels of attraction towards -1. You all of a sudden introduce a peak of 25, so it's super heavily attracted, and then it goes back to those baseline levels of 1. Okay, so that's for the deterministic bridge case. Let's explore the more general idea. It's still a working paper. We have partial results. This is quite difficult, like Europe, because the shapes of the boundaries are quite complex now. But so the key idea, so this is the problem. Okay, now the process is a randomized Gauss bridge, Gauss-Markov bridge, in the sense that we have said this is bridging this deterministic point with this random point. Okay. Now, previously, it was easier because you think about it just conditioning to a point and not conditioning, or not conditioning could be seen as conditioning to the same prior. That's just the assumption of your model gives you. Okay, you keep Gaussianity, and that helps a lot. When you condition, generally you lose that. And now, so these are just illustrations of the process. The 2 points prior, this is a truncated normal, this is a truncated normal, but in the negative axis and so on. So what we did first was, okay, let's transform this guy, applying kind of a similar transformation in terms of a Brownian bridge. So we equated that to this optimal stopping problem when that Y is a randomized Brownian bridge, meaning a Brownian motion hitting a terminal density. Not the same terminal density as the previous one, but just a transformation of that, okay? just a transformation of the one you apply in the real problem. So now by doing so, we immediately gain that all the results in the literature that are out there about the randomized Brennan bridge, we can easily extend it to this case. Unfortunately, when we say all the results, it's really just two papers. It's really just these two. This one by Long and co-authors, which is mostly numerics. It's very illustrative. He played around with different gain functions and different priors densities. And then this one is more theoretical. It's quite nice from Eric's time ago. And we are more stepping into this direction here. So what happened here? Let's see the difference. If you can come up with the dynamics of why, if you apply Glissando theory, you get this information drift that tilts your process towards the right direction to hit that terminal density. Now the idea is the difference, you lose that Gaussianity, you end up with this terra you hadn't previously. Previously you had when you were working in the deterministic case at the end, like bridging to this deterministic point, you had here just that non-random point, and now you have the expected value of this set sy, which is the updating of your pinning point after you see that your process at time s takes the value y. That is the density of that is this posterior, which is the this ratio of normals times your prior. And so you can see here you have y, so you go from being linear in y to be highly nonlinear in y. Another layer of complexity on top of that is that now you depend on the original point when you condition. You didn't have that previously in these two cases that we explore. So that's we'll see the end product of that introduction of nonlinearity. Okay, so this is an assumption we made to control the derivative of the boundary, but it's not limiting at all. A bunch of prior densities satisfy that. So okay, so immediately the first kind of outstanding, it's not, you might have expected that it's not that odd given the nonlinearity of the boundary. You have not connected stopping regions. So you have cases when your stopping region is not connected, so you're gonna have stopping, continuation, stopping, and you cannot connect 2 points of the stopping region or the continuation region. Okay, so we prove that, and we also prove a case when you do have sufficient, when you do have a connected stopping region, when you have a single boundary case, meaning that the optimal stopping boundary is a time-dependent boundary, and everything above or below that it's a stopping region. So the idea is that if your preconditioned Gauss-Markov process is attracted, not repelled from the pooling level, and you have this prior that is strongly log concave with curvature greater than 1, just meaning that you have a log concave function here times a normal 0, 1. In that case, your stopping region is everything above the optimal stopping boundary. Now, these are, we call those super informative because what you're doing basically is you are reducing the variance, the preconditioning variance, you're lightening the tails, and you are also being unimodal. These are sufficient conditions, not necessary. Unimodality, we believe here, we are working on that and proving that. We believe that it is necessary. Actually, there is an example that Eric throws in his paper, kind of saying, super intriguing, that there was two prior cases, a mixture of two normals. The only difference between one case and the other one is that the means were a bit farther apart from each other. And he says it's super intriguing that in one case you do have a connected stopping region, and the other case you do not, you don't. And when you assume you see what is happening is that you're going from a unimodal to bimodal. Okay, just by separating a bit the means of the mixture of normals. So to say these are sufficient, not necessary, we believe that you can mess a bit around with these two ones and still have get a single boundary case. This is a picture illustrating the two things. First, that notion of being not connected, either in one case the stopping set, the other case the continuation set. Let me go back and forth to do that again. And second, the evolution as you vary your starting point. I told you that now it depends on the value you had when you condition. Okay, you can see how this is a similarly easy case. The easier you can go after a bridge, going from a bridge to a 2-point bridge, equal probability, and then up to -1 or 1. Okay, but you can see that the increase in the difficulty and of the geometry of the stopping and continuation regions. Our idea here, what we're trying to prove now, is that okay, you don't have a single boundary, but you might have a set of boundaries. Prove regularity on those set of boundaries. You can see here you have one boundary, another boundary meeting at some point, non-monotonic, but anyways, and then another boundary. And in the bridge case, in the many points bridge case, you can actually compute these points when you change from continuation to stopping. Okay, so this is another slide illustrating the case where we do have a single boundary. Oh, I'm running out of time. We do have a single boundary. It's a loaded slide, but basically, this is the prior now is it's truncated normal in the positive axis, and we are just. I'm going to skip. Going to rush through this. What we're doing is fixing 2 parameters on the precondition process and varying the third one. To illustrate this single boundary case, the proposition we had about that, but also the highly non-monotonicity of the boundary. I mean, you can obtain as many inflection points as you want. You have this because this is Monte Carlo simulations. So that's why you have some green dots there. So that's our results. The more remarkable ones about the stopping region. For the value region, we had a few, but this is the one I want to highlight more. Is when we try to prove Lipschitz continuity and come up with bounds for the partial derivative of the value function, we try to apply kind of the same method that we did before, but now you end up with this extra term you didn't have previously, which was this kind of L1 norm of the 2 pinning points updated at 2 initial different conditions. And you have this degree of freedom. This is a joint density that you can choose. You can embed your problem in the probability space that you get to choose that joint density of the pinning points. And it turns out that not any joint density gives you what you wish here, what you would wish here, which is a Lipschitz bound for this guy. But if you choose the one that minimizes, which is the Weierstrass 1 corpulus, or the one that gives you the Weierstrass 1 distance between these 2 random variables, these 2 densities, you can come up with this Lipschitz bound. So we throughout the paper we play around with this idea also to embed in the bigger probability space, choosing this guy conveniently. This is another, we proved the free boundary problem, but without the smooth fit condition, still working on that. And then this comparator, this is also a nice result. If you have your priors order in the likelihood radio order, then your value functions follows this order too. And you have this relation of continuation sets and stopping sets. And that immediately bounds the case when your prior it has bounded support using the optimal stopping boundaries that we found for the Gauss-Markov bridges case. And that's it. We are now still working, especially in trying to be able to say more about the geometry of the stopping and continuation region, see how we can prove for instance, we have in mind that you can have what we call stopping continuation island. It's always connected either to the horizon or the starting point. Trying to prove what I said, that it might not be a single boundary, but it might be a set of boundaries. Perhaps our idea now is that you will end up either with a Volterra integral equation that gives you a set of unique solutions, not just one unique solution, depending on the final point, or a system of Volterra integral equation, don't know yet, and trying to prove regularity, of course, of those boundaries. On the long run, what happens if we dish Gaussianity? Also, we are intrigued. This is something that we have been thinking for a long time, is that that Lipschitz continuity looks like proving too much to just get the smooth fit condition. It's nice to get kind of higher smoothness for the boundary, but it looks like we can lower that bar. Also, we are intrigued by in general, this is also is in the back of our mind, like the convergence of the fixed point algorithms. So that's it. Thanks a lot for your attention.